All right. So now let's talk a little bit more about furnace heating elements that can be used. So now we're sort of talking exclusively about the electronic resistive heated furnaces. And so I just wanted to go through some of those common heating elements that we might see. All right. So this is a table from a different textbook that talks about some of the different materials that we can use, and it's a useful table because it can tell you the maximum useful temperature that we can use it, and also the atmospheres. Some of them work better in certain atmospheres than others. So if we start here at the lower end, we have chromium alloys, so various chromium alloys, and those are generally good to about 1300 degrees, so what we would consider low temperature furnaces. And then when we can start to get into more refractory or noble metals, those can take us all the way up to 2800 in some instances, but we'll probably cap that at about 1700, because if you look over here, the useful atmospheres, we have O, N, and R. So O is for oxidizing, N is neutral, so inert, and then R is reducing. And so if you'll notice in this, these last two do not work in oxidizing environments, which is pretty common because air or oxygen is an oxidizer. So molybdenum and tungsten are not great heating elements for most applications unless you can use them in neutral or reducing atmospheres where the risk of oxidation is less. So the best types of furnaces would be the max temperature, highest possible, and then the most versatile atmospheres, so O, N, and R. So then we go into the ceramic elements. So this is going to up the temperature that we can use them. And so silicon carbide, molybdenum sulfide are pretty common ones, and they'll go up to 1700 degrees, but you'll also notice here, if we use them in a reducing atmosphere, we can actually form the metallic components, and so that would be bad. So basically, this down here tells us about what's going to happen to the element under these conditions. You'll look at these lanthanum chromite, only used in oxidizing environments, but it goes up to 1800. And then there's some other specialized ones, and I want to sort of emphasize the graphite here, because graphite, you'll notice, has the highest temperature possible on this chart, but again, it cannot be used in oxidizing environments. So basically imagine what happens to graphite or carbon in oxygen at high temperatures. Okay, so silicon carbide heating elements are very common. They go up to 1500 degrees, but as you can imagine, it's a ceramic, silicon carbide, it's pretty brittle. And so the main hazards here are that they break quite frequently from thermal shock, etc. The graphite, like I mentioned, it has a very high melting point. In fact, it usually just sublimates, so it doesn't really melt. But again, it has some issues with oxidation, and so in fact, it's only good for reducing in inert atmospheres up to that high temperature. And the other concern is, let's say that we want to use this for a metal oxide. Well, it can in fact reduce all metal oxides at high enough temperatures. So if you're familiar with how they make steel, they use coke or a form of carbon to actually reduce the iron oxides to their metallic form. And so these are graphite heating elements are, or if you use them for crucibles, are very going to be very dependent on the materials used in conjunction with them. And so some of the materials I've actually worked on in my research show that exact phenomenon. So we actually look at this material called fiberform, which is just carbon fibers put together in a porous material. So it's about 90% oxygen. Or sorry, it's about 90% porosity. So this is when we talked about porous materials and forming methods. This is one of the materials that we could try to make. And so we've basically looked at this material because it's the basis for a reentry shield for spacecrafts. And so basically they actually impregnate this with another polymer, and then that's what appears as kind of the leading edge in these materials, in these shields that protect sort of this payload as it returns back to Earth. So these are typically unmanned applications, and the idea is that we want to be able to get these onto the Earth's surface as fast as possible. So these tend to be really high-speed reentries. But what happens is they tend to oxidize in atmosphere. So any oxygen will oxidize graphite. They use the term ablation in the NASA world, and so that's one thing to keep in mind. I've got a video here that you can kind of play on your own, but basically shows one of these plugs, as we called them, this material, as it oxidizes at a high temperature when exposed to oxygen. So I'll let you watch that in the PowerPoint if you want, but there's nothing, there's going to be no questions on that. It's just, if you want to look at that, that is up to you.